Question 6. What could be the answer for question 6? Just now we discussed this part. The, the last session I was discussing the same idea. Large Hadron Collider is designed to accelerate proton at a very high energy for particle physics experiments. Why high energies are required? Yes, C is the right answer, because if you have more energy, that energy converted into mass, so you can produce a greater mass. That's the reason why the top quark, which is the heaviest for each this quark combination, the top quark is discovered at the end, at the last. Reason for that, it's having more mass. So because we were not having particle accelerators initially in earlier, like 19th century, to produce these massive particles, that's why it took longer to discover this top quark as compared to other lighter quarks. In this question, the equation is for positive beta, which is also called positron. Use the information in the table, describe how proton changes into neutron. So basically what happened, how the proton is changes into neutron. What is a proton? Proton, we know proton is it's a baryon, which is a combination of up, and down. And it changes into neutron, so it changes into up, down, down. So basically the quark composition changes. This is a baryon. This is also a baryon. These are leptons. So lepton, the positron is there. So lepton number is for antiparticle -1, for particle +1. So lepton number is conserved. What about baryon number? Baryon number is also conserved. For each baryon, it's +1. So both proton and neutron, they have +1 baryon number. So using an information, basically how a proton changes into neutron. So you'll mention a proton is a baryon, which consists of up, and down. So the net charge is plus. It changes into neutron, which is also a baryon, and the composition changes into up, down, down. With reference to the charges of the particle, show that this decay is possible. So reference to the charges, the particle charge, because proton is positive, neutron is 0, positron is positive, the charges. So when I write the charge, proton is positive, neutron is 0, positron is also positive, and here electron neutrino, that is 0 charge, so the charge is conserved. Before and after, the charge remain +1, that shows the charge is conserved. So you can mention proton having a positive charge, neutron 0, positron +1, and electron neutrino 0. So when we check the charge on left and right hand side, it is equal, shows that this reaction is possible in terms of conservation of charge. Next part, the kinetic energy of a positron is 1.58 mega electron volt. It annihilate with a stationary electron two photons of equal energy are emitted. Calculate the wavelength of emitted photon. The masses are given. Actually, the advantage of having mass in mega electron volt per c square or giga electron volt per c square, so we can identify this is the equivalent energy which is released. So what happened? They mention a positron which is having a, this is example a positron, and it is moving, it annihilate with an electron stationary. So electron is at rest where this was moving, the positron. The mass, the rest mass here refers to like it's not moving close to speed of light, is mega electron volt per c square. And for this one also 0.511 mega electron volt per c square. And the kinetic energy is 1.58 mega electron volt. That's a kinetic energy, not c square. So they collectively, when they combine together, the total energy, like the mass which produce energy and the kinetic energy, will be responsible for production of the photons. And we have to calculate the wavelength of emitted photon. So first we'll calculate the total energy. How to get the total energy? Because when positron and electron annihilate, each of them release energy 0.511. That's the energy released by electron, energy released by positron, and 1.58 is a kinetic energy. That's also contribute to production of. That's why, like in new particle accelerators, because we can accelerate the particle to a higher kinetic energy, so this factor increases. That's why we are able to produce massive particles. So what is the total energy? When you sum them, you will get the total energy. But that total energy will divide. Why? Because this total energy is producing two photons. So each photon, the total energy divided by 2, you'll get energy of one photon. And you will use the formula E is equals to hc over lambda to get the wavelength. But the problem here is the unit. Because when I solve this, like 0.51 plus 1.58 plus 0.51 again. So when I calculate this energy, that energy is in electron volt, mega electron volt. So first, to use this formula, E is equals to hc over lambda. Energy should be in joules. So I will convert that energy into joules. Is it clear? Any doubt in this part? In a linear particle accelerator or linear accelerator, LINAC can produce electron energy up to 620 giga electron volt. Yes, the mass of electron, the advantage of this, actually, what is the advantage of representing the mass in this manner, so that we know what is the equivalent energy released by this particle. Like if the mass was in kilogram, the mass, as we know, the mass of electron is, if the mass was given like 9.11 into 10 to the power minus 31 kg. So first what you have to do, you have to first find how much energy. E is equals to mc square, and then you will get energy. But what is the advantage of this formula? Directly you will know the equivalent energy which it produce if this particle release energy or annihilate, contribute, or what fraction or what part of energy it contribute in annihilation. So that's the advantage of mega electron volt per c square or giga electron volt per c square formula. In the next part, they're saying the linear accelerator can produce an electron with energy up to 60 giga electron volt. So this is the energy which is released about 60 giga electron volt. Calculate the de Broglie wavelength associated with 60 giga electron volt electron, and at these energies, the energy and the momentum of the particle are connected by equation E is equals to Pc. So what you can do, you need a de Broglie wavelength. So if E is equals to Pc, it means P, the momentum, is equals to E divided by C. And the de Broglie, as you took in AS, lambda is equals to H over P. So after getting the momentum and Planck's constant, you can find the wavelength. Okay. Next part, experiment has been carried out where these 20 giga electron volt electrons are aimed at a hydrogen. So there's a hydrogen contained proton in the nucleus, and electron is there around the nucleus. Suggests with the reason what happened to the path of electron. So if we target, a sample is there of hydrogen, and we target this by a 60 giga electron volt electrons, means high beam of electron is there. So what we'll observe a diffraction. Diffraction means like bending of the wave. As we know, wave particle duality with this energy, like 20 electron volt, 20 giga electron volt, there is associated wavelength as we worked out. And when we find the wavelength, that wavelength is approximately same as the order of the nucleus. Like the size of the nucleus is 10 to the power minus 15 of 1 femtometer. And this wavelength, when we work out, it will be in the same order. So what we'll observe, we'll not observe that electron as a particle. What we'll observe electron as a wave. I'm drawing the wave front. So when it is passing through a sample, we'll observe a diffraction. You can also mention, because this is a wave particle duality, so you can mention if this is a hydrogen nucleus, an electron is revolving. So due to electrostatic force, the electron might deviate or change its path. That's one thing you can mention. Or you can also mention if electron is acting like a wave, then what, and this wavelength is approximately equal to the size of the nucleus. So what we'll observe spreading of the wave. We call that as diffraction. Is it clear, this idea? The diffraction. So both possibilities are there. There might be a diffraction, or it might deviate from the original path. This one is January 2015. The table gives the quark structure of the three particles. Up quark has a charge of +2/3, down quark is -1/3. composition of a neutron is given, pion is given, and delta particle is there, delta negative particle. Show that up, down, down is a possible combination of a quark of a neutron. So how you can show it's a possible combination? When you find the net charge, as you will find the net charge, because for up it is plus 2 by 3, plus 2 by 3 minus, sorry, up, down, down is there. So plus 2 by 3, minus 1 by 3, and minus 1 by 3. I was doing for proton, but it's minus 1 by 3 and minus 1 by 3. So when you find the resultant or net charge, you'll find the net charge is 0. So it shows it can be a possible composition of neutron, because the net charge of a neutron is 0. There is no charge on the neutron. The second part, state in terms of quark structure why a delta negative is classed as a baryon and pi minus is a meson. So pi negative is a meson and delta. So what's the reason? Because delta particle consists of 3 quarks, whereas pi consists of 2 quarks, and one of them is quark, another one is anti-quark. So a simple reason you will mention 3 quark combination is known as a baryon. So delta is because the delta particle is 3 quarks, that's why it's known as a baryon, whereas combination of quark and anti-quark, or you can mention 2 quarks, and in this 2 quarks the condition is 2 quark combination, but the condition is one should be quark, another one should be anti. That is refers to meson. Another particle in the delta family is a delta plus plus, is also composed of up and or down quark. Its decay is shown, like there can be up or it can be down. Deduce the quark content of delta plus plus and the charge on the pion. So it is decaying, its decays is shown. It shows that a proton is released. So how we can work out what will be the quark, the composition for delta plus plus and the charge. So to work out the charge, it's an easy thing. Why it's simple? Because you already know there is one proton. Charge should be conserved. So this should also be plus. So we identify that charge should be plus. Now what about the quark composition? So simply because it's plus 2, so the quark composition, yeah, it should be up, 3 up quarks, because they mention it's in the same family. So same family refers here that same combinations are there, same type of combination. So this will be plus 2 by 3. This will be plus 2 by 3 and plus 2 by 3. So when you solve, it will be plus 6 by 3, which is equals to plus 2. That's why the delta was having plus plus or plus 2 charge. An electron is accelerated through a potential of 3000 volts. Calculate the de Broglie's wavelength. How to calculate? First, we'll get energy. V is equal, and because voltage is work done per unit charge, or energy divided by charge. If we need energy, it's voltage multiplied by charge. Voltage is 3000, and the charge, it's electron 1.6 exponent minus 19 coulomb. That's the charge. So we'll get energy, that will be in joules. After getting this energy, we have the formula E is equals to Hc over lambda. So we have the energy, we worked out, we have the Planck constant, we know the speed of the light, so we can find the wavelength associated with this electron, which is accelerated by 3000 volt supply. So January 2014, and you can see here the rest mass of a kaon is given 494. So what you will do for that's equivalent energy will be there 494 mega electron volt. You will convert this mega electron volt first to electron volt. So 494 into 10 to the power minus 10 to the power 6 electron volt, and then convert this electron volt into joules and divide by C square. You will get the energy. You will get the mass in kilogram. In 1962, the existence of the particle with strangeness -3 was predicted. 2 years later, it was identified in an experiment involving an interaction of a proton and the K- meson, which has a strangeness of -1. A new particle was given the name omega. The interaction which conserved the strangeness was deduced with reasons. So to the charges on the omega and whether it is a baryon or a meson. So we have to deduce this with the reason what will be the charges of the omega, and then we have to predict whether it will be a meson or whether it will be a baryon, like it will be a combination of two quarks or it might be a combination of three quarks. So for first for a conservation of the charge, how we can do a conservation of the charge? What, as you can see, this is negative, proton is positive, so net charge on the left hand side is 0. K positive is there, K neutral is there. So what should be the charge of omega? It should be -1. And then whether it's a baryon or a meson, as you can see, they mention that its strangeness is -3. So if the particle strangeness is -3, means it is a combination of 3 quarks. It is not combination of 2 quarks. Because if it was a meson, then it, because meson, like example, strange and anti-up is there. So strangeness, what is the strangeness of this particle? It will be -1. But in this one question, they mention strangeness is -3 for the particle. So if strangeness is -3, it means there should be 3 strange quarks in it. And if 3 quarks are there, what it could be? This particle can be baryon, it cannot be meson. This is one reason you can mention, or you can check the baryon number, conservation of the baryon number. Like if I check a baryon number, K are the meson. So this is a meson. Meson baryon number is 0. For all mesons, any kind of meson, the baryon number is 0. Actually, what is the baryon number? For each quark, the baryon number is +1/3. And for anti-quark, the baryon number is -1. So whenever you have a meson, meson is a combination of quark and anti-quark. So it is always, meson baryon number is always 0. So kaon is a meson, baryon number 0. Proton is a baryon, so baryon number will be +1 because it's a combination of up and down. So this is meson 0, meson 0. So to have a baryon number conserved, so this should also be a baryon number +1. So if something is having a baryon number +1, so it cannot be meson, it is always a baryon. Is it clear? How we predict that this particle can be a baryon, not a meson? Then using the information given in the table, deduce the quark composition of each of the particle involved. Like we have to give a quark composition. What is this composition of a quark for K minus, proton, omega, K plus, and K neutral? The charge of omega is -1 because the conservation of the charge should be there as well. So what could be the quark composition for K minus? It's a meson. For a meson, I need quark and anti-quark. So how it can be a meson? Yeah, what could be the quark composition for K? K negative. It's a meson. We want a net charge to be -1. And if you read the question, they already give you a hint. K minus is a meson, strangeness -1. So if this particle is having a strangeness -1, for strangeness to be -1, there should be a strange particle in it, inside. But because it's a meson, so if there is a quark, there should be anti-quark. So for K minus, strangeness -1, so there should be strange particle. What else should be there with the strange so that I get a result -1, the charge, because the charge should also be -1. So if it's a strange particle, the charge is -1/3. I need charge to be -1. The net charge, it's fraction -1/3. So what I can have, I need -2/3 here. So which particle can have -2/3? Anti-up, because up is plus 2 by 3. So anti-up will be minus 2 by 3. Then what is the composition of a proton? Proton is up, up and down. Plus 2 by 3, plus 2 by 3, minus 1 by 3. So that will give us the composition of proton. Then K positive. Because they are in the same family, so it shows the similar type of composition should be there. Strangeness for every strange particle is -1, and for anti-strange it is +1. This is called a strangeness number. Up and anti-strange, yeah, that's right. For this K, it will be up and anti-strange. And for K neutral, what will be the composition of a K neutral? It will be down and anti-strange. Yeah, the strangeness number for K positive will be +1. Look, the reason why I was using a strangeness, because as I mentioned, existence with a strangeness -3. So this particle is having a strangeness -3. This particle strangeness -1. So this should have a strangeness +1. This should also have a strangeness +1, so that the strangeness should be conserved. That is why I was using a strange particle in both K plus and K0. Is it clear? This combination of the particle, how to work out the particle combination. In the question, they mention that this particle has a strangeness -3 and K minus meson, which is strangeness -1. Because proton does not contain a strange particle, so its strangeness is 0. So these particles should have a strangeness +1 so that this reaction can occur. So here, and already they mentioned it's a strange, so for a strange -1, so it contains a strange particle. This will contain anti-strange. Why anti-strange? Because in strangeness is +1 for anti-strange. Strangeness number. In another experiment involving a head-on collision between the two protons, result in the following: a proton 7 pion, pi positive, 7 pi negative, K positive, and another lambda particle is there. Calculate the minimum kinetic energy of each proton for this interaction. So basically, there is a mass of the two protons and the kinetic energy of the two protons converted into the total mass of the particles which are required. So we need a kinetic energy. So look, for example, I will get the total energy of these particles, the total mass energy which is equivalent to mass required to produce these particles, and I will know how much energy these two protons can supply. So when I take the difference, I will know how much extra energy I have to supply to these protons to produce this combination. So Simply what we have to do, we have to find the total energy required for the production of the product, and we know total energy which is available from the reactant, the two proton. When we take the difference, we will find how much energy, kinetic energy is required for this interaction. Is it clear? This so basically we can also say the total mass of the reactant plus kinetic energy of the reactant gives the total mass of the product. So total mass of the reactant, we'll sum them. Total mass of a product, we add them and we subtract to get how much kinetic energy is required for production of these particles. The interaction would not have taken place if one of the proton has been stationary and the other has a twice the calculated value. What is the reason for that? The interaction would not have taken place like if one of the proton is stationary and like if I say if two protons are moving towards each other, if the kinetic energy of this one is 20 joules, example, this is just an example, the kinetic energy of this one is also 20 joule, and the interaction occur, it was producing the particles. But if I do the same process, that one of the proton is stationary and the other proton is moving with the same total energy, which is 40, same as the initial one. So what is the reason? What might be a reason for this? Yeah, what could be the possible reason here? Like this interaction will not take place if one of the proton is stationary and another proton has a twice the kinetic energy which we calculated. The first case, it was production of the particle. Second, it does not happen. The same interaction, even though the energy is the same. You can see 40, here also 20 plus 20, 40. Any idea? So basically, what is the reason? Look, if the particle one is stationary and another one is moving, so initial momentum of a system is not zero. So final momentum should also, it should not be zero. So there will be a kinetic energy or energy used to move the other proton. But here, as the particles are moving in opposite direction, initial momentum is zero. So the final momentum will also be zero. So energy is not used up for moving the particle, or all the kinetic energy is used to create a particle. Here, not all of the kinetic energy is used to create the particles. Is it clear, this idea?